All right, so section 9.2. It's all about vectors. And so you've all had physics at this point in your career. Typically think of a vector as something that has magnitude and direction. So obviously velocity comes to mind, displacement comes to mind, acceleration, force, all these things. You need to tell me how much, and you need to tell me which direction it's going. Okay. That's not new. That's not different. We've been drawing them for years. Perhaps it makes a 30-degree angle at the horizontal, or perhaps the guy took off and he was going at a 42-degree compass heading. Okay, where this is 0 and 90 and so forth, to the east and so on. Okay, same thing, same premise, same thing you've done for years. And you talk about, oh, how do I add vectors? Oh, I'm glad you asked. Here's A, and here's B. What? That looks goofy. Don't write B there, Jay. B over here. Attaboy. Excuse me. Yeah, there's B right there. Attaboy. So I'm going to add them. I'm going to take A, which is right here, like so. And I'm going to put B, tail to head with them, like thus. Nice. A, B. So this is A plus B. That's hot. And of course, that is also a vector. And of course, we said it's tail to head. That's how we add them. Okay, some people say tip to tail. I find that's annoying. I like tail to head, but you do you, friend. You do you. And so, obviously, back in the day, you'd go, oh, yeah, so, well, let's see here. First thing a person would learn in physics, typically when you do one of these problems, this is a 40-degree angle. All right, cool. And this was 37 newtons of force. Right on. The first thing you'd do is you'd break this baby down to pieces, and you go, all right, cool, this is 37 cosine 40. And this guy here, like so, it'd be 37 sine of 40. And you're like, all right, I can do this. Probably, yeah, I hope so. Come on, Jay, make sure that you are in the proper mode. Oh, but of course, on the next problem, I'll need it back in degree radians, and I'll forget to change it, because that's who I am. Bam, 28 newtons in the horizontal direction, and of course 37 sine 40, 23.8 in the vertical direction. Wow. And so what have you done? Well, you've taken this and you found the components of the vectors, okay? And we can actually write them thus: 28, 23.8, where this is our delta x and this is our delta y. And it's same premise, same idea. It's no big deal. And so we're going to get used to writing them this way. In fact, it doesn't matter where we start. Okay, here we are. This could be at 0, 0. Cool. If it was, then we're going to end up at 28, 23.8. Obviously, this is going to be a point up here. That's a point because we went from here to there. That's right. That's right. Wait, what if I started at 5, 2, Jay? That's a great question. If I started at 5, 2 and went 28 this direction and 23.8 this direction, well, excuse me, well, I feel like I would now be at 33 in the x direction, and I would be at 25.8 in the y direction. Whoa, that's cool. Hey, wait a minute. Is it true, Jay, that if you were to take this point here, which would be their final point, let's say x2, y2, and this is x1, y1, and you were to take and find, I don't know, x2 minus x1, oops, 1, and just find that, and you were to find y2 minus y1, wouldn't that just be equal to our delta y and our delta x? That's right. And so couldn't we just write that as a vector, delta x? I already wrote it up there. I mean, couldn't I write that as something like this? And the answer, of course, is yes. That's always true. Okay, so if one were to have started from here at the point 3, 1, 9, how do I know it's a point, Jay? Because it's got parentheses around it. And I were to travel over here to, I don't know, -6, 19, -2. What was my vector? I don't know. It's a good question. I started at 3. I went to 6. That's negative 9. I started at 1 and I went to 19. That's a difference of 18. And I started at 9. I went to negative. That's a difference of negative 11. But didn't you say the minus? I did. Negative 6 minus 3 is negative 9. 19 minus 1 is 18. Negative 2 minus 9 is negative 11. That's hot. Question, how far did you go? How far did you go? Or, if you prefer, what is the magnitude of this vector? I don't know. Wait, yes I do. It's 9 squared plus 18 squared plus 11 squared. Notice I just said screw the negatives for right now. It just makes my life easier. Oops. Moving a distance of 22.9. And we call that the magnitude of the vector. Okay. So let's just do another one here. Let's just do this. Let's say we start at point A. Point A is located at 2, 4, 5. And we go to B. Actually, we're not going to start at B. We're going to start at B and we're going to go to A. So we're going to go from B to A. Oh, that's hot. So that would be 2 minus 3 is negative 1. So again, we're going to end up at A. So it's 4 minus 7 is negative 3. And 5 minus 10 is negative 5. Question, what's the magnitude of this guy? I don't know. Yes, I do. It's the square root of 35. We will write that as the magnitude of BA. Question, is it the same magnitude as from A to B? And the answer, of course, is yes. Why? Because AB would be 1, 3, 5. Same distance, opposite direction. Nice, nice. And I don't think anybody's terribly shocked by that. Let's say that this took 2 hours to get there. All right. Is that fast or slow? Yeah, I don't know. Let's just keep going, like we were here. We went from, that's true. We went from B to A. So we went from B, we went to A. That's hot. And it took us like 2 hours to get there. Or would we be in another 2 hours? I don't know, but I feel like it'd be the same distance out there. Are you with me? It's twice as far. Maybe we end up at D out here somewhere. I don't know. Whoa. Like how far did we travel total? I don't know. It'd be 2 times that AB or BA distance. It's the same. So 2 times the square root of 35. And we call this guy right here, you may recall him as the scalar. Now, what does that mean? It means you just scale it up or down to make it fit. Okay? You just scale it up, scale it down. Give me more. Ooh, that's too much. Oh, I need to go faster. Okay, I need to go slower. Okay, whatever it happens to be. Cool. Yeah, for instance, you're like, oh, Jay, did you take a long walk today? I did. Did you walk, in essence, 2 miles this direction? I did. Not really, but yeah, we'll pretend. And then did you walk this way about 1 mile? I did. And if this was Kansas, could you have gone twice as far that direction and twice as far? I could have. It's not Kansas, but we can pretend. I guess. I'm not sure why I'd want to. But we could pretend that it was Kansas. And I'm going to redraw this a little further down the page. I got room to work, okay? So I went 2 miles. Sweet. And then 1 mile. Nice. Notice that is completely to scale, by the way. No big deal. 2 miles. And so you ended up from here to here, right? So square root of 5 miles. That's right. Whoa. Could you have gone twice as far? Again, if in Kansas, I could have done that, yes. And what could I have done originally? I could have gone up twice as far originally and twice as far over originally. Or I could have gone same thing, right? Same procedure. Okay, so if this distance, if this was the vector A, was this guy right here, then the magnitude of A would be square root of 5. And then 2 times that magnitude is just twice as long. Duh. Not very hard. Okay? So be aware of that. That's very straightforward. It's stuff that you've seen happen, of course, over time. It's nothing new. Okay? Again, going back to physics or somewhere, you've seen these kind of vectors like so. Cool, whatever. What if I wanted to do A minus B? What would I do? Well, I would take A, which looks like this fella. And I would take B and I'd flip him around the other direction. I'd write him like so. And so this guy here would be A minus B. I'd just flip him around. Okay. Now, what does that mean, Jay? Well, I'm glad you asked. So, for instance, this guy here would be something like, check it out, -3, 0. In other words, it's just in the horizontal direction, let's say. Do you buy that? Looks just horizontal to me. This fellow looks like it's -2 and -3. Okay. So if you look at this guy, you're like, I feel like we ended up below where we started. I agree with you. Because to get to here, I feel like we're below where we started. I agree. But I feel like we're to the right of where we started from. And that just seems weird. But does it, friend? Does it? Because check it out. What I see here is I went -2 this direction, yes. And I went down 3. Cool. And then I took the opposite of this guy, the negative of this, which is going to be +3. So over 3 we go. And we didn't go up or down. So when we look at this, it's going to be something like this. -2, -3. I'm going to write it like this for a minute. Minus. Wait, are you saying that all I literally have to do is go -2 plus 3, -3 minus 0? Yup. What? That's it? That's it, kid. Nothing to it. Nothing to it. Is that also true for adding vectors if they're already in component form? Yep. Wait, so you're telling me that if you had A and it was just this guy here, and you had B, it was just this fellow right here, whatever, and you wanted to do 2A plus B, no, minus B, then literally all you would do is take 2 times this, and you get 4, 34, 12, and then you would just subtract these guys. Jay, could I distribute the negative? You could, or you could just subtract. So 4 minus a -3, and then you get 34 minus 1, and you could do 12 minus 2, and then lo and behold, you'd have 7, 33, and 10. Done. Escape. Jay, show us in the 3D calc plot. Can you do that? Can you do it? Can you do it? Can you do it? Would love to do it for you in here, friend. If you click in here, you can just add a vector. See? Pretty sweet, pretty straightforward. Where is my stupid keyboard? I lost my keyboard. There it is. I found it. We're good. We're good. All right, cool. Check it out. So my original vector was... I'm going to write... Well, I'm going to do a different one with smaller numbers. How about that? Is that okay with you? I'm going to do it anyway. I don't care. I'm going to use smaller numbers because otherwise it gets a little tricky. It's not tricky. You can change it. I just don't want to change it. I'm feeling like I don't want to. This is A, and then this is B. Let's just do A plus B, because why not? Sure. Nice. And so, by the way, in the books, the vectors will be the dark, bold, lowercase letters. I will use the vector symbol on top of them when I'm writing them, when I'm doing it for my lesson, because I find it easier. People don't tend to screw it up less if you do that. So 3, 2, 4. Watch me do this. I'm going to come in here and go boop, 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 boop. 3, 2, 4, like so. Now, you can change, if you like, and I do like, the color, and you can make this a thicker line or something. And oh, that's nice. Sure, sure, sure. And then you can come in here, and what was my other one? -1, 0, -3. Now, I want to show this because a lot of people will screw this up. And they will mess this up bad. And they'll be like, I don't understand what I did wrong. Well, you didn't do it right. That's what happened here. Like, what? Those are not tip to tail, Jay. And I 100% agree with you, friend. Notice how the first one started at 0, 0, 0. The orange one started at 0, 0. They both started at 0, 0. But that's not true. What should happen is the purple one should start at the tip of the orange one. And since the orange one started at 0, 0, 0, it finished at what? Do you see that? I can make it start wherever I feel like making it start. Nice. Now, what was the final answer? I forget. 2, 2, 1. Wasn't it? 2, 2, 1? So that would be the same as if you had started at 0, 0, 0 and gone to 2, 2, 1. Oh, that's not going to work. Ah, babe. What? Look at that, huh? Isn't that hot? That's kind of cool, I think. All right. I think it's helpful. I think it's nice to visualize. I don't know that it's 100% necessary, but I think it makes me feel better about it, to be quite honest with you. Just makes me happy inside. Would it matter if I took A plus B or A plus B? Would it matter if I flip-flopped them? And no, the answer is no. It wouldn't matter at all. So, oops, I didn't hit shift hard enough. Sorry about that. Cool, they're the same. In other words, it is the commutative property holds for these guys. And by the way, since we just saw that when you're doing addition, you're just adding the components, and addition is associative, would it matter which order I added them? And the answer, of course, is no, not a bit. Yeah, and you're like, oh, whoa, that's cool. Wait, what if I just had a vector and I added the 0 vector to it? Oh, nothing's going to change, bruh. Wait a minute. What if I took A and I added its inverse to it? No way. You mean like I left home, I went straight to work, and at the end of the day I came straight home, and my net displacement is a big fat goose egg? That's right. Big 0 right there. That's cool. What if you had C times A plus B, and you're like, wait, what does that mean? Why doesn't C have an arrow on top of him? Because C is a scalar. In other words, you could scale them both up first and then add, or you could add first and then scale them up. Looks a lot like the distributive property, because it kind of is. Yeah, exactly. Wait, could you do the same thing with scalars and then multiply them by a vector? You certainly could, friend. You could take C times A plus D times A and then add them up. Same premise. Well done. Well done. Could you also times the two, could you also multiply the two scalars first and then times it by A? And the answer, of course, is yes. Could you take one of the scalars times A and then multiply it by the other scalar? And of course, the answer is yes. Why is that, by the way? Well, because it's all multiplication and addition. And everything we've just talked about in those are, all it is saying, hey, look, that is a, what do I want to say there? All that is the commutative property and the associative property of multiplication. And I mean of addition. And so if you think about that, it makes perfect sense. Years ago, teaching algebra 1 one day. Oh, it was years ago. Gosh, I bet that girl's in her mid-30s right now. Last I heard, she had a couple of kids. Be interested to see her now. Some of these kids that just left, and some of them an indelible mark on you. You're like, I wonder what she's like now. But anyway, one day I was trying to get her to say addition is commutative. And so I'm like, addition is, starts with a C, addition is, and she goes, communicable. And I went, oh, for God's sakes. That's herpes. Wow. No. So going back to Algebra 1, you learned about the commutative property of addition and multiplication, and the distributive property, and the associative property. That's all we're doing here. These are the exact same formulas. I'm not going to bore you with the timesing by the 1, because if you times by 1 doesn't change anything. Duh. That's also the multiplicative identity. I'm not going to bore you with that. Now, earlier, I wrote something like this down, and you were like, Jay, I get what you did there. I get it. It was the delta x's and the delta y's and the delta z's. Well, that makes sense, Jay. I'm like, I know. That's why I did it. And so you're like, oh, cool. Interestingly enough, we're going to introduce in this text, in this chapter, the combination of these guys. And you're like, what the heck are these guys, Jay? These guys are what we call the unit normal vectors. Unit, because they are 1 unit long. Normal, because they are, normal is another way of saying orthogonal or perpendicular. They are orthogonal to one another. Okay? In other words, this guy is in the x direction only. This guy's in the y direction only. This guy's in the z direction only. Okay? Only. So tell me, if you had I plus j plus k, and you wanted to add them together, what would you get? You get that. Wait, what? Yeah, because you just add them. 1 plus 0 plus 0 is 1. 0 plus 1 plus 0 is 1. And then 0 plus 0 plus 1 is 1. That's amazing. I know, right? So question. What would 3i plus 2j plus 5k equal? That's a great question. And the answer is, it would be 3, 0, 0 plus 0, 2, 0 plus 0, 0, 5, which would be 3 plus 0 is 3. And then 0 plus 2 plus 0 is 0. And then 0 plus 0, plus 5 is, it's 5, dummy. Wait, 0 plus 2 plus 0 is 2. Good Lord. Hey, look, it's the same one. Yes, indeed. Indeed. And which one do you prefer, Jay? I prefer this one. 95% of the time. The other 5% of the time, there's one reason and one reason only that I prefer this method. But they're both correct. So you do you, friend. Jay will never get angry about it. I might mock you a little. No, I wouldn't do that. To each their own, man. If this is the way you like it, man, you do it that way. I just don't care. Okay? Understanding the book does it both ways just to see if you're paying attention. 2, negative 3, 7, Ri. No, that's not true. What the back of the book has is you have 2i minus 3j plus 7k or whatever. And the back of the book has 2, negative 3, 7. No, you get the same. To just quit having a fit about it, okay? Why do they do that? I think to see if you're paying attention, to be honest with you. Again, there is one place, really in one place alone, where honestly I think it makes sense to do it that way. And it's for doing cross products by hand. When you're doing a cross product by hand, why, yeah, I think that's the best way to go about it. I honestly, it's the only real way to go. So, funny story. Some years ago, my kid went to college, freshman year. He's now 24, yeah. And so he's in his class, and of course, the idiot professor, you will not use a calculator. I'm like, oh, for God's sakes. Yes, because it's 1975 again. All right. Even I got to use a TI-81, for heaven's sakes. Look it up. It wasn't good, but it's better than nothing. And they said, oh, yes, you must do this. And they showed me how to do a cross product. And he told me the formula. I'm like, good night, nurse. So in other words, they're memorizing this goofy formula. When instead, if you just learn what the formula is about and go, oh, so a cross product is just a determinant? That's right. Oh, that's easy. I know. But instead of that, they just gave you this goofy, ridiculous formula, which included 3? Yes. Well, no. It was 6 addition and subtractions and multiplication. Well, no, I don't know. There's a couple of 1, 2, 3, 4, 5, 6 multiplications. Well, actually 7, 8, 9. That's a lot. And you had to memorize it all. And these minus this times this times this minus this times this times this plus that times that. Are you kidding me? And instead, where did that came from? It came from doing the determinant. And so I will show you my way of doing the determinant, and I will use the I, J, and K for that personally. Okay? It's pretty straightforward. That's how I want to see it done. And there you go. Okay? To me, that just makes the most sense. Excuse me, I'm going to die, I think. All right, cool. Now, a couple things from the homework here, a little discussion. Oh, one more thing I wanted to show is this. We just mentioned the unit normal vector. And the unit normal vector is, again, a vector that is in just the x direction or just the y direction or just the z direction, but it's 1 unit long. So if I said to you, I was going to go from here to here, and I'm just going to do another one of these guys because I think it's fun. I'm going to start at this point, and I'm going to go to this point. Then my vector would be 5. From 1 to 2 is 1. From 5 to negative 3 is negative 8. This would be my vector. Sweet. What is the magnitude of this vector? I don't know, but it's not 1. It's the square root of 25 plus 1 plus 64. Good criminy. Oh, it's 26. So 9. Square root of 90. I thought it was square root of 100. I was going to get really excited for a minute. Square root of 90. Well, that's hot. And you're like, well, what does that mean? It means it's the square root of 90 units from here to here. That's right. That's right. That's right. But, you know, sometimes it would be nice not to have to worry about the length of it. It'd be nice if you could just tell me the direction. And so the direction simply would be a matter of saying something like this. What if I were to multiply this guy by 1 over the square root of 90? In other words, that'd be 5 over the square root of 90. 1 over the square root of 90. Negative 8 over the square root of 90. Now, what is that going to do? It's going to be in the same direction, but it's going to be 1 unit long. Okay? And we like these kind of vectors, right? We like them. They make us very happy. This is A. Now, the way we write this guy is going to be this. It's going to be A divided by his magnitude. This is a unit vector. It will now be 1 unit long. This is going to be 25 over 90 when I square this thing. 1 over 90, 64 over 90. And what happens when you add that up and square root it, you're going to get 90 over 90, which is 1. Square root is 1. Ta-da! That will always be true. We will use that technique of finding unit vectors for several things. They're very important. Okay. Oh, I don't know. Should we do that one here? That sounds like a fun guy to me. You know. Do I want to do that one? Yeah, let's do this one. That sounds fun. Find the unit vectors that are parallel to the tangent line to the curve y equals 2 sine x at pi over 6, comma 1. You're like, what does that mean, Jay? I don't know. Let's find out. So we're going to find the unit vectors that are parallel to the tangent line y equals sine of 2x, or 2 sine of x rather, sorry, at pi over 6, comma 1. What does that mean? Good question. Let's go look at Desmos. Okay, I don't know. It's too late in the day to do any math. Boom. Well, you know, oh, it's pi over. So what did I say? Pi over 6, comma 1. Let's put a dot on the map, shall we? A little dot on a state road map. Nice. Well, that's hot. How would I find a what do I want to say? How would I find how would I find the tangent line slope? It's a good question. It's a good question. It's not really. It's an easy question. Y prime to cosine of x, yes? So let's plug pi over 6 into that guy. What do you get? 2 cosine of pi over 6. Well, the cosine of pi over 6 is, and that's square root of 3 over 2, I believe. So it's going to be 2 square root of 3 over 2, so you get the square root of 3. That is my slope. You're like, oh, okay, what does that mean to me? Well, last I checked, slope is equal to rise over run. That's a J-Room official spelling right there, friends. That means the Y is going to top. Get it? All right, so if you think about this, what that means is we got the square root of 3 over 1. Another way of saying that, of course, is a delta Y over the delta X. Now, no way. No way, Jay. So you're telling me, Jay, that I'd have a vector starting at this point that's right here, that is pi over 6, comma 1. I would have a vector going like so with a slope of square root of 3, which would be this guy right here. I'm like, yep, that's right. But I could also go this way, and I'd be also on that tangent line, yes, which would be negative 1, negative square root 3. Nice. That's it. Just getting you to think about these different pieces and parts and so forth. I don't know. What do you got here? So find the unit vectors that are perpendicular to the tangent line. Oh my gosh, perpendicular? No way. Well, perpendicular lines have what? Perpendicular lines and vectors have negative reciprocal slopes.
So it would be 1 over square root of 3 negative. That would be the slope of the perpendicular line. Huh. Well, wait, that would be this would be the y now, and this would be the x. That's right. So you're saying it would be something like either, it'd be kind of going down like this or going up like this, yes? Well, look what I did. I went in the x direction, positive. I went negative in the y. Yeah, so I could have done this. Oops, I did it backwards, you moron. Sorry, let's try it again, Jay. Or could have gone negative root 3 and then up 1. Ta-da! Now, again, just kind of cool. I liked some of the ways this guy did it. Old, bless his heart, old Stewart here, he's been dead for about 10 years now, but he used to just get all kinds, I don't know who's getting all the money from his books now, but it's pretty sweet. Okay, pretty sweet. I kind of did graph them all. I mean, here's my curve. What? There's my curve. There's all my vectors. Isn't that neato? All right, great. I did want to mention one thing, and that's this, is that vectors to me, I mean, yeah, I taught physics for a long time, about 20-something years now. I like vectors. I get them when it comes to adding and subtracting vectors and forces and all that good stuff, torque, that kind of thing. Matter of fact, I think the thing that every now and again, you just, something stands out in your mind. You're like all of a sudden, every piece fits. Like, for years you do something, you're like, yeah, that makes sense. And then you're like, yeah, that makes sense. And then all of a sudden, just out of the blue one day, you're like, kaboom. So I don't remember when it was, probably 5-7 years ago now. I was building an engine one day. And a lot of you probably, I don't know, if you never built an engine, you wouldn't know this. But inside of an engine, the main bearings, there's always one that has what's called a thrust bearing. And because your crankshaft will actually move back and forth in the engine a little ways, a few thousandths of an inch. And none of the rest of them have that wear pattern there. Only one of them does. And I always knew it was there, and I understood that it does walk backwards and forwards. But in my mind, I was thinking that it only was because no one ever told me why it was there or why the crankshaft moves, and or that it always moves on every engine. I only torn up ones with standard transmissions at that time, I guess. And so I think someone maybe years before told me that mostly because when you push the clutch in, you can actually have that causes the crankshaft to go in and out, and that is true. But every car will move backwards and forwards. And you're like, well, why does that happen? It's a good question. Because torque. Okay? Torque, remember, is a vector. Okay? Why is torque a vector? I'm sorry, not torque. Let me backtrack a minute. Let me back up just a minute here for a second. So we know that torque is a vector. Let me just back that up and just talk about it. Torque is a vector. And we know that it is, the way we've always looked at it, is force times a lever arm. Okay? But if you recall, it matters which way the force is acting, right? And so if you've never seen this before, if you had a bolt that's going this way and you're turning a wrench clockwise, you're applying a force this way. Well, what's the nut going to do? Well, the nut's going to walk itself down the bolt like that. Okay? In other words, it has motion. Like that's because of the threads. Yeah, the threads are on there because of that. They go with that motion. Okay? And so in matter of fact, when we get to there later on, we'll talk about being in the right-hand rule and stuff. But interesting to note, that was the first time that it dawned on me that when you accelerate your engine, because torque also has to do with acceleration, and when you accelerate your engine, that crankshaft is going to, as it is torqued and you're forcing it around faster, and if you step on the gas and you're going really fast, or you back off super fast, either one, it creates a torque. And because of that torque, that crankshaft will move one way or the other in the system. And I think that was the time when like all the pieces started to fit for me, and I'm like, whoa, that is so awesome. Because you think about things in one aspect, you think about something somewhere else in a different aspect, but you don't really put all the pieces together sometimes. And when that happens, you're just like, what just happened? Today I went for a fairly long walk this morning, which I do most mornings if I have time. And while I'm out there, now mind you, it's 5:30 a.m. I'm just kind of chilling, just relax and do my little walk. And the weirdest thought came to my mind. They still do it. I don't raise hogs anymore, but when I used to raise hogs back in the day, we didn't. We did ear tags, but a lot of guys would still, and they still do it these today. They do ear notching, which is just a way of identifying the pigs. But it's a base 3 numbering system. And I've known that for years. I didn't really think about it, but duh, okay. It's a base 3 numbering system. And that's kind of a neat, weird thing. And I remember when I was a kid, we just learned how to read them. And I thought to myself today, how cool would it have been if my ag shop teacher had worked with my math teacher? Then I remembered, wait, Jay, you've been teaching for 25 years. You know why that wouldn't happen. Because the math teacher has no clue that that's a thing, and the ag teacher doesn't realize that's math. And so the two never come together. Okay, but it's one of those deals where like it all came together, and you're just like, whoa. You could have taught us idiot farm kids like base 3 arithmetic. It would have made sense. And you could have taught us logarithms and stuff, and that would have made sense. But no, you're just sitting there going, oh, yeah. And if you ask some old grizzled farm guy, he'd be like, oh, that's number 29. You can tell because it's got one mark up there. It's got the marks right there, you see, and one of the 27s are marked out. And then down here it's got 2 on the 1s. And you're like, yeah, no, I get it. But like, do you realize that's base 3? What are you talking about? I'm like, yeah, exactly. So there's just days when everything fits and all the pieces come together, and that's great. And that's what I like about it. But more importantly for me than physics and everything else is statistics. Because mathematically, that's where my heart is. Okay, I love statistics. Don't get me started talking about my degree. It still pisses me off. Thank you, Portland State. But anyway, it's just for the best. I don't care. Anyway, in statistics, we talk about vectors a lot. And so what I will do is I will go out and collect some information. So I will ask people, hey, how old are you? Cool. All right, cool. What do you weigh? I'm not asking. Don't get all upset. Yes, I don't really care. I'm just going with it here, okay? Yeah, okay. And excellent. Yes, and your weight and your cholesterol, sure, cholesterol, something like that. And then I will say, cool, sit down over here and I will take your blood pressure. Bam. And we're going to take the systolic because I don't care. Nice. These will be my X values. X1, X2, X3. And this guy here will be my Y, my only Y. Okay? And the idea here is I'm going to sample something like 100 people. I don't know. And so what I'll end up with is three X vectors and then another vector for my Y. And then we have a fellow up here named Adam. And Adam will actually have a vector. And it'll be something like this. It'll be 27. He'll be 200 pounds. I don't know what a good cholesterol is. Sure. And sweet. And that, oops, why did you write like that, dummy? And that will be a vector for Adam. Nice. And so Adam will have a vector of data. And then also I'll have a vector of ages. I'll have a vector of weights and a vector of diastolic or cholesterol levels. I better write that nicer. I can't even read that. Cholesterol. Nice, something like that. And so when I look at this, I think to myself, okay, that's neat. What's that going to do for us, Jay? Well, here's the game. In statistics, this vector here needs to be orthogonal to this vector here. It means independent. And it also needs to be independent of this guy here. Meaning it'd be weird if when you change someone's age, their cholesterol changed. Meaning that's what it would mean if it was dependent. Meaning that if my as I got older, I got fatter. Oh, that is true. Sorry. But you get the point. Okay, you get the point. And so the idea is that we want those guys to be independent of one another. Okay, so that allows us to tease out the differences. Which one of these guys, or which one of them is having a significant effect on Y, and exactly how much of an impact is it having on Y. So from a vector standpoint, and behind the scenes in statistics, we do a lot, and I mean a lot of linear algebra. We do a lot of calculus. And behind the scenes, all that gets done, and you're going, oh, cool, look at that. Did you know, Jay, that I could predict the blood pressure for a guy who's 27 years of age and 200 pounds and 130 cholesterol? I could predict what his blood pressure is or whatever. And you're like, no, this guy's is 120. Yeah, his is, but I could actually come up with an equation that would predict for everybody's. And you're like, whoa, how did you do that?
Well, behind the scenes, we're dealing with these 3 x vectors and then this 1 vector of y. And to me, that's the biggest deal, okay? I never really grasped the concept because we didn't have 3D back in the day, graphing software. Heck, we barely had 2D graphing software. And so it was really difficult to grasp exactly what that meant. We talked about things being orthogonal. Yeah, I'm down with that. What does that mean? Well, it means they're perpendicular. And I'm like, well, who gives a rat's fanny? Oh, I see. That's how you can tell if things are independent. Yes. Oh, gotcha. Perfect. That starts where everything starts to make more sense. And for some people, like, just draw me some graphs, Jay. Draw me some lines, add some vectors. Cool. Good. Awesome. For other people, you're like, oh, I dig that algebra. Just add a plus, 3i plus 2j plus 6, whatever. That's cool too. But in this class, I want you to get to feel for all of it. Okay? And that's what's going to be kind of a neat deal of it. Now, we're not going to do a ton with statistics, but I'm going to continue to come back to this. Later on, one of the places that we'll get to talk about this a little bit more is in the case of when we get to multivariable integration, like triple integrals. And everyone's like, well, when do you ever use triple integrals? Well, you really don't. The only place I've ever used them is in statistics class. Because you're talking about, when you're doing integrals, you're finding probability. Okay? And so in integrals, you're coming back to that statistics. And that's the place where I continue to try to bring it up to where people are like, oh, yeah, that makes more sense. Instead of this weird, oh, cool, I found a triple integral. What does it mean? Well, technically, you found the hypervolume. Okay, what does that mean? Well, it doesn't really mean anything, but all right, cool. Yeah, but in one place that really matters is in the statistics thing. And again, I've never done more deep calculus and more deep linear algebra applied than I have when I was doing statistics, my master's degree stuff. Okay, so again, I will bring it up from time to time. We'll talk about it. We in statistics, we always talk about our vectors, these vectors, and we talk about that a ton. So I just want you to be aware that it's not always just your grandpa's vector here from back in the day. Look at that. All right, let's add that guy up or whatever. We're still going to talk about that kind of thing, but that's not as much. We're not going to focus on that all the time. Okay. Yeah. So that's kind of where we're going with there. That's for 9.2. 9.3 and 9.4, we started getting into where it gets interesting. We're going to take these vectors and we're going to do different things with them. In 9.3, which we'll be doing in the next video, we're talking about the dot product and so forth. And so we're just, again, continue to work our way through. Once you understand what a vector is, then we can do a lot more cool things with it. For instance, we can find angles between a couple of vectors. Would that matter? Geez, I think it would. Could you do just, find some good uses for some of that stuff? Yeah, sure. Yeah, for sure. Mm-hmm. So we're going to kind of talk about that. We're going to work our way through it. Chapter 9, you feel like it's not calculus yet. No, it really isn't calculus yet. What it is laying the groundwork, if you've never seen it, for 3 dimensions and looking at vectors. Okay, because once you understand vectors, you're like, oh, wait a minute, Jay, I feel like if you had this guy here, let me back that up. I feel like if I told you I started at 3, 2, and I said I went on a vector of 2, 4, okay? So I started here, I went on this vector. Could you tell me where I would be in one, let's say in 1 minute? And you're like, well, I wouldn't know, Jay. Oh, I'm sorry, back for I tell you. This means, let's say this is 2 meters per, well, actually it's 2 seconds, okay? Let's do, where am I in 1 second, okay? So you're like, well, I don't know. Well, I forgot to say this is 2 meters per second. This is 4 meters per second. You're like, oh, well, that makes sense then. Sure. So then I would be at something like this. I'd be somewhere like at 5, 6, yeah? Are you with me? And you're like, well, I am with you, Jay, except that I'm not sure, like, am I at a point or am I at a vector? That's an excellent question. It's an excellent question. So here's my question, here's my answer to that, okay? Can you add a point with a vector? And the answer is, well, no, not really. So let me just say this to you. Check this out. So if I were to do this, if I were to put a t on the end of this in 1 second, right? So I put 1 second here. Check this out. I would go 2 meters per second, 4 meters per second times 1 second. Whoosh, whoosh, whoosh. And you're like, I'm adding meters plus meters, Jay. I'm like, no, I agree. No, I agree. I 100% agree with that. So I get meters and meters. No, I understand. But watch carefully. If I'm at 3, 2, 1, 2, 3, 1, 2, right here, and then I go over 2, 1, 2, 1, 2, 3, 4, and then I'm up to here now, you're like, cool, nice. But where does this 5, 6 represent ourselves? Okay, well, here's what I want to suggest to you. What I want to suggest to you is this. Let's make 3, 2 a vector. Well, where is it a vector from? Oh, it's a vector from the origin. Interesting. Nice. And from that guy, let's then go on 2, 4. And let's go out one length of time from there. Sweet. So when I add those together, what I get is this resultant vector, which would be then what? It would be the vector, not the point, the vector, you see, 5, 6. That is from the origin up to there. Okay? Now you're like, well, that's kind of interesting. So what you're saying then, Jay, is that we're going to go 3, 2 plus 2, 4 t. And I'm going to say, yep, that's what I'm saying. And then wait, but Jay, couldn't I distribute this because you gave us that formula earlier on? Yeah, you're right. But wait, isn't this just 2 vectors? Couldn't I write them together? That's right, atta kid. Atta boy or gal or whoever the think you are. I'm so glad you're in my class. Well done. You listened to me. I can't write, but I'm so pleased that you're here, that you've got me so wound up, I can't even write thoroughly. Wait, Jay, that's a function. Yep. Wait, so is that? It is. You're not wrong. Wait a minute. Wait a minute. This is like, I don't know, what do you call it? I don't know, h of t? Sure, I guess. Why not? But wait a minute. I feel like whenever we had h of t or something like this, I feel like we did a lot of derivatives back in the day, didn't we? You know it, pal. So can we do h prime of t? You better believe it. 2, 4. Ah, nice. Nice. And we will do that and so much more in chapters 10, 11, and 12. That sort of thing. So in chapter 10 in particular, we're going to do a lot of what I just did here, but obviously more. Pretty sweet things like that. Chapter 11 has to do with derivatives, but in a different way, not with vectors per se, but with functions. And then chapter 12 has to do with finding not area under a curve, but volume under a curve. But again, before we get there, we have chapter 9 is all about getting comfortable in 3 dimensions with graphing, getting comfortable with what vectors are, what they look like, and then realizing that you can have vectors that do all kinds of goofy things. For instance, you could, in theory, do this. You can come in here and go, oh wait, stop. You could click on, wait for it, space curve. What? Look at that, huh? Look at that, will ya? Watch this, friend. Watch it go. There I am. Wait, there I am. Here I come. Whee! Nice. That's hot. And so this is r of t, but it's the same thing I just wrote in essence. And look, it's x of t, y of t, z of t. In other words, what they have that written as is cosine t, sine t, 0.1 t. Yeah? And so, of course, they just wrote this as r of t, and we will use r primarily instead of h. But that's the same premise. And you're like, what? Yeah. And then you're like, wait, where am I? I don't know. Somewhere. How fast am I going? I don't know. It feels like a derivative question. Well, how fast am I accelerating? Ooh, that sounds like 2 derivatives. Can't fool me, pal. And so we'll do a ton of that. Okay. But again, chapter 9 is all about laying out the groundwork for that. So that's why you think at first, like, gosh, this doesn't feel very calculus-y, because it's not yet. All right, enough.